everyone! We are Senior Design Team 7, and our project is to fabricate a 2-layer tubular structure for 3-dimensional cancer cell culture and microtissue analysis. Our project advisor is Dr. Oshino, and we are glad to have the opportunity to work in his research lab for this project.
I'm Arushi Mathur.
And I'm Megha Shankar.
Throughout the presentation in the divider slides, we've included photos of the two of us working in the lab to look out for. The second leading cause of death in the United States is cancer, a constantly evolving disease with over 200 distinct forms. It is characterized by rapid tumor growth and unpredictability. Treatment and management for this condition is incredibly expensive, and research focuses on developing treatment options with a minimized focus on the testing process for the treatment options themselves. It's important to understand the difference between a flat 2D environment versus a 3D environment in addition to the benefits to constructing a model like this. A flat environment is not as useful in understanding cell or tissue behavior versus a 3-dimensional environment, which is a better indicator of tumor and surrounding tissue behavior. Also, hydrogels have been shown to be a good 3-dimensional cell culture environment, with the main benefits that they will maintain similar mechanical properties, they are a cheaper alternative to using live animal models, and the timeline for testing is sped up, and there's much more repeatability. Our problem statement is to develop an in vitro model that mimics cancer cell proliferation and migration behavior, in addition to studying the interactions on the 3-dimensional level. Our objective is to design and fabricate a 2-layer tubular structure to study cancer patterns ex vivo.
For our design, we developed an in vitro model for measuring in vivo conditions consistent with those in metastatic cancer. Our design will model cell tissue and cancer metastasis interactions by allowing the observation of cell proliferation and migration patterns. Overall, through this project, we aim to bridge the gap between testing after drug production and use in a clinical setting. In this diagram, the 2 layers of the design are highlighted, the inner layer consisting of collagen, MCF7 breast cancer cells and agarose, and the outer layer that is created by microdipping this inner layer in a sodium alginate hydrogel solution. The design is very small with width, length, and height dimensions of only a few millimeters. A key tool utilized in creating this inner layer is a capillary micropipette, which has 2 components involved, a plunger and a capillary tube. As the plunger is placed in our hydrogel solution, it draws up the material in the solution within the capillary tube. Therefore, the inner layer is created by utilizing this capillary micropipette. Once a homogeneous solution of both the collagen, agarose hydrogels, and MCF7 tumor spheroids are combined and created, using this micropipette, the spheroid which is now encased in this hydrogel solution is collected, forming a tubular structure.
Here's an example of a spheroid encapsulated in this agarose collagen hydrogel, which represents our inner layer.
The methodology behind our outer layer is a micro-dip coating method, where the tube created for the inner layer is submerged in a sodium alginate hydrogel solution to coat the inner layer, which is then placed in a calcium chloride solution to cross-link the structure created.
These are images of our MCF7 breast cancer cells at different points in time. Here are images of different spheroids that we created in the lab.
Before creating a homogeneous solution of both agarose and collagen, we had to test various agarose concentrations to determine the desired concentration to use in our design. By comparing 0.8%, 0.9%, and 1%, a 0.9% agarose concentration was neither too soft or too firm, which would allow for maximum cell proliferation and migration, in addition to best representing human tissue conditions. Here are images of our early prototypes of our tubular structures, consisting of an outer layer of sodium alginate hydrogel and an inner layer of agarose without the incorporation of MCF7 breast cancer cells. Through this crucial step, we were able to test and perfect our protocol before the addition of any cells to avoid errors in our protocol. Mechanical testing is the next step in our project after our design fabrication, which will allow us to apply stress on the hydrogel and live cells by utilizing micro tweezers, which are shown in the top left image to study potential deformation patterns, which will help us to better understand the tumor microenvironment.
Throughout the semester, our work was primarily focused on developing the methodology for an adequate 3-dimensional structure to culture MCF7 cells. A particular emphasis was placed on the hydrogels we used and their properties, maximizing cell proliferation and migration, but we also prioritized keeping the costs low and reproducibility. Our results from the experiments conducted will allow further evaluation of the structure's abilities to interact with cells and maintain a homeostatic environment that enables cell survival. This also simulates cancer cell migration through healthy tissue layers. From this, the mechanical and biological properties can be classified in detail, such as the deformation, stiffness, and biocompatibility. In the future portions of this research, our goal is to introduce small quantities of drugs to assess whether the model created is suitable to predict drug behavior in vivo. Running drug assays with this model will hopefully provide opportunities to observe potential metastasis inhibition.
And finally, we'd like to thank the following people for all their help and support throughout the year.